being recorded.
Well, welcome,
hello everyone,
everyone.
and welcome to Quasi's second Cyberseminar of the 2013 fall semester. My name is John Pollock, and I'm the User Support Specialist here at Quasi. It's always fun for us to see who our audience is for these seminars, so if you could take a moment to please type your name and affiliation into the chat window, we'd really appreciate that. Also, if you could take a moment to please mute your line for the presentation, it'll be a great help in cutting down on the background noise. I'll be online this afternoon to monitor the Adobe Connect room to make sure everything goes smoothly. But at this point, I'd like to introduce Todd Rasmussen, who is a professor of hydrology and water resources at the University of Georgia, and also a member of Quasi's board of directors, and has graciously agreed to host this fall's Cyber Seminar series.
Okay, thank you, John. Welcome to everybody for joining us. We focus this semester in some of the talks on early career scientists, and today I have the privilege to introduce Laura Erban at Stanford University, who will give today's Quasi Cyber Seminar. Laura received her undergraduate degree in environmental sciences at the University of Virginia, and then spent 2 years with the U.S. Geological Survey at Woods Hole, where she studied submarine groundwater discharge using naturally occurring radioisotopic tracers. Her graduate work has since been at Stanford University, where she is now completing her doctoral degree under Professor Steve Gorelick in the Environmental Earth System Science program. Her research and the subject of today's presentation is on arsenic contamination of the multi-aquifer system underlying the Mekong River Delta in Vietnam and Cambodia. And thanks, Laura, for speaking today.
Thanks, John, and thanks, Todd, and thanks to all of you for listening in. So yes, today I'll be speaking about arsenic, which is a highly toxic and abundant crystal impurity in deep groundwater in the Mekong Delta, and this is part of the widespread arsenic crisis in Southeast Asia that you may have heard of, which continues. Arsenic is a common groundwater contaminant found in aquifer systems around the world, but the health risks it poses to humans are particularly concentrated in South and Southeast Asia. Here, more than 100 million people, the majority of them living in Bangladesh and neighboring West Bengal, India, but also in Pakistan, Nepal, Myanmar, Thailand, Cambodia, Vietnam, and China, are estimated to be exposed to drinking water with arsenic in it, drinking water that's drawn from below ground. And that huge population derives in some part from the fact that large populations are settled in high-risk areas, namely the rivers that drain the Himalayas and the Tibetan Plateau and deposit arsenic-laden sediments on their floodplains downstream. So I work in this floodplain, the Mekong River Delta, which is home to over 20 million people living in Cambodia and Vietnam. And here, as in many of the other arsenic-prone basins of the region, groundwater use has been rising dramatically in recent decades. Now, if we look at the number of wells installed in the southern Vietnamese portion of the Delta over the past several decades, we see a phenomenal rise that's due to a lot of factors. Interventions by international aid organizations, socioeconomic growth, and political stability, particularly here in South Vietnam. There's the influence of the end of the Vietnam War in 1975 and economic reforms that followed. And in these parts of the world, groundwater offers a very attractive and dependable source of water in regions that are characterized by low hydraulic infrastructure and high seasonal variability in the availability of surface water. And we can see those changes in seasonal availability of surface water from space. So this is dry season satellite imagery. You can see clouds in white and dry and arid areas in brown. And in green, you see either swamps or flooded fields. Cambodia appears pretty parched during the dry season. Its fields are fallow, while Vietnam does considerably better due to an extensive network of canals. And the Mekong River, which forks first here at the Cambodian capital of Phnom Penh, and then into numerous other distributaries in the Vietnamese Delta, is confined to its channels. Contrast that with the rainy season of the Southeast Asian monsoon, when water breaches the banks of the river and floods many kilometers in every direction for several months of the year. Now, you may have trouble even seeing that flood because it's so full of sediment it appears brown. So if I manipulate this image now, same image, but now the sediment appears pink to you, you can see it, and the rest of the flood is pink and purple here, and then sediment plumes being shot offshore that are helping to build the delta out to sea. Here's the river channel for comparison. Now, these extreme changes in water availability throughout the year dictate how and where people live in the delta and how arsenic came to be a problem here. So if we focus now on a smaller area near the river in Cambodia, looking now at the kilometer scale, we can start to think about the water supply options for households. You can even see some of these households lined up along the levees here. So during the dry season, the wet season rather, households may collect rainwater in pots or cisterns, is commonly done, or store it in backyard ponds, divert river water into canals, or pump it from tube wells. During the dry season, they can access these other storages, but this one won't last very long. It's also subject to contamination from whatever's on the roof, and if it's not covered, by roving animals and children. And these ones are carry a considerable pathogen load that's likely to make you immediately and or violently ill. And this option offers a convenient and affordable water supply, as a well can be drilled in your backyard in a matter of hours at a reasonable price, and the water that comes up is available year-round. It looks and smells safe to drink, and it won't make you sick from arsenic poisoning for several years, if at all. Now, arsenic can be safely removed from drinking water, as is commonly done in the U.S., where groundwater arsenic is also a widespread concern, and other developed countries. But the other major contributor to the Southeast Asian arsenic crisis is that groundwater typically goes consumed without receiving any treatment. And you can treat it in this part of the world, too, using special filters. But there are a variety of impediments to the adoption of that technology. And arsenic that's ingested chronically is linked to a variety of health ailments, including cardiovascular disease, neurological impairments, skin lesions, skin cancer, and internal cancers, among other ailments. And the risks of those conditions are multiplied if you smoke or have nutritional deficiencies, as many do in this part of the world. But the symptoms of arsenic poisoning don't manifest for about 2 to 10 years, making well water a very rational choice given the other options. And in fact, not all wells are even contaminated. Here in a high-risk area near the river, about 1 in 2 actually are. These are actual data from a partner NGO in Cambodia. And the arsenic concentrations vary considerably. So the World Health Organization's drinking water standard is 10 parts per billion, or ppb. That would mean anything in blue is acceptable according to that standard. But wells with concentrations up to 1,000 ppb or over that, which is 100 times the safe declared limit, are found in close proximity to wells with no arsenic at all. So your well may be fine while neighbors may be toxic. So you may ask the question, how does arsenic get into these wells in such variable concentrations? Well, that has to do with the complex interplay between hydro-biogeochemical conditions in the subsurface. In these contexts, arsenic release occurs mainly below the water table, where microbes in the subsurface dissolve the minerals that are binding it, namely or predominantly iron oxide minerals. You can think of those as rust, if you like, and microbes in the process of degrading cobaried organic carbon will run out of oxygen and turn to other materials for respiration, including iron and arsenic itself. So these minerals dissolve in a process referred to as microbially mediated reductive dissolution. And now this dissolved aqueous phase arsenic is free to move with the flow of groundwater and contaminate wells. And the landscape is basically discontinuously loaded with reaction chambers where the favorable conditions for arsenic release are found. Wetlands make especially good reaction chambers, wetlands like oxbow ponds, which are abandoned river meanders, and depressions in the landscape like interior wetlands, where floodwater never completely recedes, and these wetland features efficiently collect and bury fresh organic carbon from aquatic plants and other sources, and create the favorable conditions for arsenic release and have the favorable hydraulic gradients to push released arsenic into underlying aquifers. So a conceptual diagram of that process might look something like this, where now we're looking at a suction into the earth, as if I've exposed a depth profile, and we have aquifers in blue and capped by confining clays in gray. So I'll be using this color scheme throughout the talk. And we have an incised wetland here in the most shallow superficial clay, creating a plume or volume of contaminated groundwater in the shallow aquifer. Now, wells are variably contaminated because they're basically sampling different water masses, some into which a plume of arsenic may have been released, and others that are sampling the background water mass of clean groundwater. And that heterogeneity in concentrations persists at the regional scale as well. So these are data from the Vietnamese Department of Water Resources Management, and they're part of a nationwide survey that I had to go to Vietnam to get, and it took a good deal of legwork before going, finding the data. They're really just a tremendous source. I mean, the richness, you're looking at over 40,000 observations for the south of Vietnam that have not been available online or in published work before. And that's kept me very busy. It's quite a lot of information to exploit. And the spatial coverage of these wells is really quite remarkable, both in 3 dimensions, across space and over depth. You can see the Mekong River is shown here in white that passes under the majority of the purple and a lot of the dark red observations, where the most high-risk areas are nearest to the river. But the problem with looking at these observations in 2D is that you can't appreciate the depth of the wells. And in fact, they are sampling from 1 of up to at least 7 distinct aquifers. So here I'm going to make the aquifer system transparent. You're looking at bedrock underneath, and let you have an appreciation for the spatial structure of these wells. I spend a lot of time just doing this because I think it's really the best way to be able to see 3D data and appreciate them. So if we do this now, we're starting to see a cluster of deep orange contaminated wells. These are about 10 to 50 ppb in general, and they're spatially contained without wells around or above this cluster that are contaminated to the same degree. And so that is an interesting observation that I'm going to try to highlight using this concept of a focus area. So it's a strange shape that is a boundary for all those deep contaminated wells, and really any in the vertical stack of wells defined by this shape. So it's really a focus volume, but I'll refer to it as a focus area for simplicity. And this area is over 1,000 square kilometers in extent and contains nearly 900 wells at depths of 200 to 500 meters with arsenic. And that extent and severity of deep contamination is really unique. It's never been observed. In all other basins, the tendency is for the mean contamination and proportion of affected wells to diminish with depth. And that's to be expected for 2 main reasons. The first is, as you drill deeper into these systems, you're getting into older sedimentary layers where the reactants to dissolve arsenic are becoming more recalcitrant. So dissolution rates slow down. And secondly, as you drill into these systems, you get into older aquifers that have experienced longer periods for natural flushing. That is, groundwater is always moving from upland areas to the coast, flushing these systems. And so for these 2 reasons, slowing of dissolution rates and increased flushing, deeper aquifers should have a greater degree of natural remediation. But the focus area profile is much different. And I became really intrigued by this, recognizing that outliers often make great subjects of study, and here I have so much data to study. So if we take a closer look at the focus area, here is the actual stratigraphy rather than that idealized perspective I showed earlier. And you can see an incredibly complex system of really extensive and thick confining clays that are separating and interbedded with the aquifers themselves. The deep observations in the focus area, the deep contaminated cluster, falls within the deepest 3 aquifers here. And here is the boundary at the top of that deep aquifer group. So I'm going to divide the focus area again into shallow and deep aquifer groups, or zones. Now the shallow zone has Holocene to Pleistocene age aquifers that are from the modern to about 2.5 million years old, or from the present to 2.5 million years old. The deep zone has Pliocene to Miocene age aquifers that are 2.5 to up to 20 million years old. And I make this Paleo-period classification distinction because it's often used as another characteristic of aquifers in these contexts, because different Paleo-periods are associated with different paleoclimatic conditions that in turn have consequences for the way carbon was buried and consumed and what mineral forms may exist in the aquifer today, with in turn consequences for arsenic release and retention. And we'll return to that concept later. But for now, I can show you the observations in the more convenient 2D scheme since I've classified them to these zones. And I'm using the same color scheme for arsenic as before. I've added a yellow color for low 5 to 10 ppb concentrations and grayed out all the observations less than 5 ppb outside the focus area to help you see it better. Now you can see that the contaminant burden is much less significant. The mean concentration is less in the shallow zone compared with the deep zone. So the shallow zone just appears bluer to your eyes. And that is very significant because in the past, when arsenic has been encountered at unexpected depths, it's often been attributed to deep pumping that induces vertical transport of arsenic or arsenic mobilizing solutes from the near surface to depth. So the blame would be that the shallow zone is responsible for contaminating the deep zone when deep pumping happens. But these observations don't support a shallow source. And if you calculate flow rates through this incredibly complex system in which the clay layers are making the vertical path really difficult by their low permeability, those vertical flow rates would also not support transport of shallow contamination to the deep zone. Now that doesn't necessarily mean that deep pumping is off the hook. And in fact, one of the eureka moments in this work came from looking at pumping intensity of those deep wells. So here the darker colors are higher pumping intensity, and that's estimated using the age of the wells and the district aquifer unit pumping rate for these wells. So it's a volume over the time period that these wells have existed. And you could basically draw the same focus area shape, right? I'll just toggle it on and off, suggesting that pumping is having an influence here. So just possibly not in the way that has previously been thought. At this point, you really need to think about where water for deep pumping wells comes from. And we'll walk through that. If I install a well into a deep aquifer and screen it so that it's only open down here in the steepest unit, so that's where the water will enter the well. When I install this well in a confined aquifer, typically water will rise on its own to the level of the land surface or above it. So I'll indicate the water level in blue. When pumping commences and continues, the water pressure in that deep aquifer will decline. And the water level in that well, and indeed in neighboring wells that may not even be pumping, that goes down too. So now the weight of the overburden, or the sediments and water overlying that deep aquifer, feels comparatively heavier because the water pressure in the deep aquifer is no longer helping to support it. So these sediments compact. The clays are typically squishier than the sand, so they're the weakest link, and they're going to give and release water to the deep aquifer that helps to satisfy that pumping demand. And any solutes that are in that water being expelled from clays will also be expelled. So I like to use the analogy of a dirty sponge, basically being wrung out at depth and squeezing those solutes to the underlying aquifer. So we have clay compaction at depth, and that's evidenced as land subsidence at the surface. The land slumps to accommodate that new space. So now, updating our conceptual model from earlier, I'm including now pumping, clay compaction, and land subsidence, and this deep clay compaction inducing these plumes of arsenic in this deep aquifer. So you may be asking, what reasons do we have to think that these deep clays are contaminated like dirty sponges? And there are, in fact, a number of lines of reasoning. For one, we know that shallow Holocene clays in the Mekong Delta mobilize and retain high concentrations of arsenic over long time scales, since these low permeability clays take a long time to flush. And after burial, so now we're down in some of these deeper layers, the gradients for that vertical flushing of arsenic or arsenic mobilizing solutes are pretty much erased. So this flow direction basically, or this gradient becomes less consequential than lateral flow through the aquifers themselves. And that is how, if you'll recall, that's part of how deeper aquifers got naturally remediated by long-term flushing. So these Pliocene and Miocene clays were likely deposited under similar paleoclimatic conditions, or similar climatic conditions to the modern, because the climate during that period was as warm or perhaps warmer than the current period, suggesting that, well, we know that sea levels were high, lots of wetlands storing lots of carbon anoxically, burying lots of carbon anoxically, such that the biogeochemical conditions during those periods may have been analogous to those we see today. And in addition, we don't see, from the observations, we don't see aquifer concentrations that are as high or higher to the deep focus area wells, suggesting there's not an arsenic source in the aquifers that's really likely to be responsible for this deep contaminated cluster. So it stands to reason that it's the clays that are the source. And in fact, when studies have been done in multi-aquifer systems, most of the studies I'm aware of pursuing natural solutes in these types of layered systems have found higher concentrations of those solutes, irrespective of solute type, in the confined clays compared with the adjacent aquifers, because presumably this inadequate flushing of the clays is, in fact, is what happens over very long time scales. So the support for this deep source mechanism of contamination draws in part from hydromechanical modeling as well. So I constructed a 3D model of the region surrounding the focus area and reconstructed the 3D stratigraphy within it. I have two types of layers, clay and aquifer, that are assigned homogeneous properties with a modest anisotropy for the aquifers and a specific storage, which is related to compressibility for the clay layers that is 10 times higher than for the sand layers. So they're 10 times squishier. And I monitor the response to pumping of this model with these monitoring wells at these nests indicated in these circles, circle colors. And I pumped this model from 1988 to 2008 in 2-year stress periods I'll talk about in a minute. But just to describe what these nests are that I'm referring to, so at each of those circle locations is a nest where multiple wells are each tapping different aquifers. And this is great because it allows you to have knowledge of vertical and horizontal gradients to compare your model with. Here are some actual data from one of these nests, and this is quite typical to see that the shallowest aquifer is, the heads are oscillating seasonally, but there's no long-term trend in drawdown, whereas in the deeper aquifers there's a slight seasonal oscillation, but the trend among these observations is for increasing drawdown over time in a more or less linear way. In fact, the greatest drawdown is most often seen in the deepest aquifers. Now, assigning that pumping I referred to before was perhaps the most challenging component of this modeling exercise. And we wanted to assign pumping in a spatially and temporally explicit way. So I used the installation year of the wells again, and that we know the pumping rates only for 2007 at a district and aquifer specific scale. So the districts are about 10 kilometers on a side. There are many of them in a space like this. But it's not, those are kind of large areas. So I work out a unit pumping rate for each district aquifer combination in 2007, and I turn each well on at the unit rate where it's found in the installation year. So these, basically in this model, wells are coming online all the time or every 2-year stress period at the unit rate that I specify. And in that way, we recreate the 3D, some sort of 3D spatially and temporally explicit pumping schedule. That's not perfect. Of course, wells pump at different rates over space and time, but it's a good approximation based on what we know. And I use this 1996 cutoff as an illustration of the fact that wells in the focus area are much older, on average, than surrounding areas, about 10 years older, roughly. And that's part of why we saw the pumping intensity metric was higher within it. We'll return to that point later as well. And so, without trying to recreate those seasonal oscillations, we really capture the 3D changes in drawdown quite well with this pretty simple model that I've described. So here you're seeing each aquifer in a distinct graph, and they're color-coded by the nest. So across this domain, we're capturing those trends in hydraulic head that are defined by pumping. And the model would predict that subsidence is occurring in and around the focus area at rates of about 1 to 2.5 centimeters per year. But because that model is based on a number of assumptions, most importantly the unknown properties of the subsurface materials, it really could use an independent check. And there are no ground-based observations of land subsidence here, so I had to estimate them another way. And the way that I estimated measured the subsidence rates in this region is using an approach called interferometric synthetic aperture radar, or InSAR for short. And InSAR has been used for many different types of land deformation, including earthquakes, landslides, volcanic events, ice flows, and to study land subsidence due to the extraction of oil and other subsurface fluids like groundwater. So it's a commonly used approach that's based on radar data that can give us an independent check on the model results. Now, very briefly, what InSAR does is measures radar waves returned from the Earth's surface on 2 different passes of a satellite, between which a deformation event has occurred that I'll denote with delta Z. So the sensor on the satellite sends out a radar wave and returns the backscattered radar signal, recording its amplitude and phase. And when there's been a deformation, there's also a phase shift in the wave that's recorded by the sensor that is a direct measurement of that deformation. So after we correct that phase shift for error terms, then we can relate deformation to the phase shift using the wavelength and a factor of 4 pi that accounts for the 2-way travel time of the radar wave. So the difference in data acquired on these 2 dates, when I take the complex difference there, is referred to as an interferogram that I'll be using to measure deformation. Now, that sounds really simple, right? So in addition to the fact that it took me over a year to get my first results using InSAR that I can understand, it becomes even more difficult approach to apply in the Mekong Delta. And that's because the idealized bounce back of the wave I just showed you really only applies to nice, stable surfaces like rooftops or roads or packed clay. But in the Delta, we often have a flood, in which case the radar wave hits the flood, bounces in a different direction, does not return to the sensor. You don't get much signal. And much of the rest of the Delta is covered in rice, grown in one of up to 3 cropping seasons, and it's flooded as well. So radar waves bouncing off the flood, off the stalks, off the top of the mature rice is going to give you a signal that looks like the land surface is changing when it's not. So a lot of our landscape in the Delta is incoherent, and we only get usable signal off a relatively small fraction of it that is developed. So I just wanted to prepare you for some of the patchiness in the InSAR results that you're going to see. And I also mentioned that we have to correct for different sources of error. So we always remove a phase shift that's due to topography. And in fact, topography was one of the first reasons for using InSAR. We can make digital elevation models because the satellite sees the landscape from different geometries that induce a topographic phase shift. Now, that's not really important in the Delta, which is flat, so it's a negligible correction for us. There are also commonly orbital errors due to the fact that we don't always know the precise locations of the satellites, and because of that, there can be a phase shift that looks like a linear, looks like this, like a linear phase ramp that's imposed in the interferogram, and this can be readily modeled and removed. By far the most challenging error is due to the atmosphere, and specifically the water vapor burden within it, which imposes spatially and temporally variable phase delays in the interferogram that we don't know. And you can measure those phase delays from the ground using GPS, but we don't have those measurements, and as I said, the atmospheric errors will vary over space. So I used an approach to minimize that unknown atmospheric and random noise component that's referred to as interferometric stacking. And what stacking does is makes interferograms on multiple interferograms that try to capture the same amount of deformation in each. So let's say I had an earthquake in July. If I have image pairs on either time side of the July event, they should see the same amount of deformation. And when I average those, using as many interferograms as I can, then I'm going to beat down that noise because it's assumed to be random, and the signal that I want to see should come out stronger. So stacking is basically a phase averaging approach that helps us with the unknown errors. And the data that I used for this were from the ALOS PALSAR instrument from the period of availability of 2006 to 2010. And I chose a time interval for interferograms of 1 year. So image pairs come from anniversary dates. And that's because I want to get a long enough time period to try to capture a deformation signal because land subsidence rates, as we saw with the modeling, are expected to be small. And I also want to use anniversary pairs so that they're in the same phase of the hydrologic cycle. So I'm capturing that downward linear trend and not mixing up dry and wet seasons when hydraulic heads are oscillating and not having the same downward slope. So I stack together as many anniversary paired interferograms as I can in the following results. And finally, I want to select only the high quality InSAR estimates. As I spoke about before, I'm going to point out where they are. So places like Ho Chi Minh City are very radar bright. The image here is InSAR amplitude. That's like a radar brightness of the scene. And the levees and the other smaller cities in the Delta are raised up above the flood, and they're forming a developed network that will give me usable radar signal, compared with the Mekong River, which is pretty radar dark, and the paddies themselves. So I use another parameter called InSAR correlation, which is related to amplitude, that is just basically a measure of agreement between neighboring pixels, and I threshold the following InSAR results at a correlation level that readily distinguishes the open water and paddy from the developed network. So these are the InSAR-based subsidence estimates in and around the focus area. The scale here is centimeters per year, and 0 to 3.8, with red being the highest subsidence rates. Ho Chi Minh City clearly stands out, as do some of the other major cities in the Delta. And there's generally diffuse subsidence on the order of 2 centimeters per year occurring in and around the focus area. To compare the two subsidence rate estimates, I'll show you the InSAR results on the left here. The middle panel, those results are upscaled to the 1 square kilometer resolution of the model, and then finally the modeling or simulation results here. Now we see that there's generally good agreement in the magnitude and shape of the subsidence results from both methods. We have diffuse subsidence in and around the focus area, although your eye may be drawn to some of these areas outside of it that are high as well. And there are a couple reasons that we could see that and think back to the arsenic data set. So for one, some of the districts that are down in this area south of the focus area did not report well measurements at all. So we don't know what's going on there with respect to arsenic. And then recall that around the focus area, many of the wells were considerably younger. And it's possible that they are inducing subsidence. Remember, these are recent rates from 2006 to 2010, but that contaminant transport to the wells has not had time to take effect. So the wells in the focus area were about 10 years older than in surrounding areas, and maybe it takes a decade for those solutes to get to the wells. So at this point, I've kind of wrapped up what we consider to be the suite of evidence in support of compaction-induced contamination being responsible for deep contamination in the focus area. And you may ask, well, what about other areas? Is there any evidence that's occurring elsewhere? And as with everything I've talked about so far, the answer is complicated. In fact, most of the other high arsenic observations are found in shallow aquifers. This conspicuous region is largely shallow contamination. And in shallow aquifers, it becomes much more difficult to separate the natural and anthropogenic components that may be causing it. And we could get there with field studies, but at the regional scale, it's just very difficult to say. Then there are other areas of the Delta. You'll recall Ho Chi Minh City was heavily pumped and subsiding, and also the Khao Mau Peninsula down here in the southwest, where heavy groundwater exploitation is occurring, drawdown is happening, and we don't see arsenic anywhere really in the profile. So here the thinking is that these are depositionally distinct from the central delta, and that basically we'd be squeezing a clean sponge in these areas. They're not as prone to arsenic contamination, so we wouldn't see the same response during pumping. So at this time, the only cluster that I can definitively link to compaction-induced contamination is in the deep focus area. Now, the findings of this work are, first, that there is pervasive deep arsenic contamination in wells in the Mekong Delta. This was unknown and a surprising result in and of itself. I've also proposed a new mechanism of contamination that may be responsible for these observations and may be occurring elsewhere. I further demonstrated the use of InSAR as a reconnaissance tool for detecting potential areas of compaction-induced contamination. After you find out what the subsidence rates are, you need to follow up with ground truthing, but it could be a nice way to start looking. And I finally demonstrated the success of using InSAR in a very challenging region. And that's important because often InSAR is applied in areas where it's more easy to do. The conditions are more favorable. But there are many other interesting parts of the world where we may want to apply InSAR that it can be successfully used. So now, what are the implications of this work for water resources management? I think first, we of course need to understand the nature and occurrence of deep arsenic and how widespread or general this mechanism I've proposed may be. We could also site wells strategically in areas that are low risk with respect to arsenic and monitor them, and we could screen them in intervals of aquifer that are far from the confining clays to minimize their impact. And it's, of course, possible to treat or blend contaminated groundwater. The technological side of removing arsenic is a solved problem. There are other impediments to being able to treat it, but it's possible. And finally, I think the work argues for a need to limit intensive extraction in these contexts. Forget about arsenic for a moment. We can still induce land subsidence and saline intrusion in these types of aquifer systems. And these are vulnerable regions that are near sea level, that are prone to flooding, and where agriculture is extremely important to livelihoods. So the small deformation rates can make big differences. So for those reasons, we need to limit intensive extraction, and then layer onto that we could also be exacerbating the arsenic crisis. I think there's a strong case to be made to be limited in our use of deep groundwater. So with that, I would like to thank you and also give thanks to Quasi for the opportunity to give this webinar. It's been my pleasure. To my co-authors and advisors, Steve Grelick, Scott Fendorf, and Howard Zebker. To the government agencies in Vietnam who graciously provided data for this work. And my funding sources, the UPS Foundation and School of Earth Sciences here at Stanford, as well as the National Science Foundation. Over here is my contact info. I am always happy to talk about this and other topics, so please jot down my email address and send me a line if you're interested. Thanks very much.
Well, thank you, Laura. That was a great presentation. I'll open it up to questions now. There's two ways. One is to unmute your phone and simply ask the question over the phone, or to type something in over through the chat box, and I can relay that. Laura, can you see the chat box at this point?
Let me look. Should I cannot. Should I stop sharing my screen?
You can either stop sharing your screen or have Todd read them to you. Either way will work.
I don't mind just reading them to you. That way you can move back to slides if somebody has a question. I had a quick question.
Sure.
Are there any other water quality indicators like conductivity or redox or something that people could use at the well scale to determine? Have you found any correlations?
Yeah, so that's a great question. Within the arsenic survey, the data that I showed, we don't have those parameters for every single well, but we do have other monitoring efforts that are done on a much more coarse scale, so hundreds of observations in the delta rather than thousands. And you can start to map those water quality parameters, mainly as you're saying total dissolved solids is the one that I have most abundantly, and with that you can start to look at like where the water masses may have come from, if there's buried or ancient marine deposits, and start to think about the correlations there. But we don't have the information at every well.
Residence times for those deep aquifers, have you done any estimates of groundwater age in those?
Yeah, so I mean, you can get at it through modeling, and there have been consulting groups that go in and have done C14 dating, but that, of course, will die out pretty soon. The deeper aquifers, you really can't age that way. So, I mean, it could be hundreds of thousands to millions of years, but it's a little bit unconstrained.
Who are the deep pumpers? Is that for agricultural uses then?
So, excuse me, mainly the deep pumping wells are for municipal and industrial uses. They're considerably more expensive to drill, and agriculture seems to be mainly, in most parts of the Delta, agriculture suffices on the canal network, which is really quite extensive. The exception to that is in coastal areas where surface saline intrusion makes the water quite salty, and they'll use deep groundwater for all kinds of things, including, surprisingly, to freshen shrimp ponds. I guess shrimp ponds do better in brackish water, so in coastal areas you'll see it for aquaculture. But generally the purpose of use of the deep wells where we're looking at is municipal and industrial supply.
So Stephanie Wong asks, thanks for a great presentation. How did you choose InSAR as your source of data for this study? Did you consider other satellite data?
Sure, that's a great question. So InSAR is the best satellite data source for measuring deformation, and one of my co-authors here, Howard Zebker, has been involved in developing the method since some of its earliest days. So we had a really great resource to work with, and Howard had made available, his expertise and his resources to do it. So that's really the best source of data for measuring deformation, and the ALOS satellite in particular. So you could ask, there's lots of satellites that collect radar data. The ALOS data, the wavelength of it, is particularly suited to agricultural regions. And of course, the time period overlaps with a good time period for us to measure the highest rates of deformation. So that's the reason. And also, almost as a last resort, if we had ground-based measurements, that maybe we would have used those and not pursued the InSAR, but there were just no other measurements of subsidence in this part of the world.
Another question, how about the response of the Vietnamese government? Are they sensitive to this issue?
Sure, certainly. Before I became interested in it, they were collecting, the well observations, and they are the ones who gave me all the hydrogeologic data to be monitoring the aquifers and the well logs and everything else. So they're acutely aware of the problem and the scale of the problem, and have been going to great lengths to collect the kind of information you need to start thinking about it. I think then the problem becomes one of management, and on that side I think it's harder for the government to keep up with regulation of wells. There are laws on the books, for example, to regulate pumping, and people are supposed to have permits, but in reality then you have to have funding and staff, and you need to follow up those laws with teeth, and I think that's been really a hard thing for the financially challenged government to be able to do. So yes, awareness is there, and then action and implementation is more challenging, I think. And so far, everyone who has provided data for this work and who I've worked with overseas has been really receptive and grateful for the results of the study, which you saw the citation on every slide because I have to respect copyright. But yeah, I think those are the challenges, implementation.
I know in Pakistan, hundreds of millions, or at least tens of millions of people show exposure to chronic arsenic poisoning. Do you see that in Vietnam and Cambodia then?
Yeah, so there are starting to be reports out of Cambodia that I'm aware of arsenicosis. I have not seen that much epidemiological information coming out of Vietnam, so I can't really speak to the arsenicosis situation there. But presumably, it's occurring there as well, but I don't know how well it's been studied.
Well, we're coming up on the top of the hour, and thank you, Laura, for the presentation. I hope other people, if you have questions, feel free to email Laura about them. And good luck on your dissertation defense that's coming up. And
thank you.
I'm hoping other people will,